the next unit starts the, I guess, second big part of the lecture, where we give up some of the correctness criterion for our algorithms and try to get further speed ups by doing so. This will keep us busy for a while, and in the first bit, we'll kind of set the stage mostly for the algorithms with a few examples and basically some terminology. So I'll give a little bit of motivation and maybe a deep dive in one specific topic just to make a point. Might keep us busy for today, and then we'll revisit a bit of the background. What's this about? Well, if we're faced with a hard optimization problem or an NP-hard decision problem, and all the known algorithms that we can think of still don't really help us in that they're still too slow, the only way forward seems to be to make compromises on what we want. Classical algorithms, as we've studied them in fixed parameter tractability, have to be always and exactly correct. And really think of exactly makes sense for optimization problems more than for decision problems. But really these are two separate properties, and we could give up either of them or both. And here we'll give up the first one, namely that the algorithms always work, or provably always work. And I guess the opposite of that is that they can occasionally fail. Now that sounds not too good, so we'll have to make sure that fail is in a specific way. For a deterministic algorithm, what fail means is that on some inputs it doesn't work. That's the only thing it could mean, because it has to do the same steps on the same input each time you run it. And that's maybe not so satisfying, because if your input is one of those that your algorithm fails on, you're still out of luck. So in a way, it's clear we have to do something that even if I give you the same input again, the next time you run the algorithm, something different will happen. And that's what we call non-determinism, because the algorithm is not deterministic, or the computation is not fully determined just by the algorithm and the input. On the other hand, I've marketed non-determinism when we discussed traditional complexity as something that's completely unrealistic and useless in practice, and just a hypothetical thing you can compete with. So we won't use general non-deterministic Turing machines here. But I think it's useful to think of randomization as a specific way of non-determinism, but one where you have control over how likely things are. And formally, it'll look quite different, but I think this is still the way to kind of see what fail means. We use random bits to guide the computation, so there's some assumed module of the machine that can generate randomness, and we won't discuss much what you can do there in practice. But this is both a solved problem and kind of not a problem, and a big problem, depending on what exactly you need. Getting some random bits is not that hard. You can measure the resistance of the voltage of some resistor. There's some randomness in there just from, at the end of the day, quantum physics, and you can calculate random bits from there, and they're true random bits for all that we know. On the other hand, if you have very specific requirements, and in particular if you need a lot of random bits in a short time, you might have to do something smarter. We'll come back a little bit on that, but for our computational model, mostly we'll just assume that there's some random bits. Now, the point of randomization is that instead of failing on some rare inputs that might still be the ones we care about, we rarely fail for any specific input. And by repeating, we can make it rarer. Okay. Why could this possibly be useful allowing something to fail, I mean, apart from making things worse, there's some somewhat distinct reasons why this can make life easier for designing algorithms. And we'll see examples of each, but maybe it's useful to already kind of distinguish them first. It often makes algorithms simpler. And simple is a complicated term. I'm currently program committee chair for a track of an algorithms conference that specifically invites simple algorithms or simple proofs of existing algorithms. It's actually a tricky problem. What does simple mean? It's in the eye of the beholder. But when you see examples, maybe you can agree that some are indeed simpler than the alternative that cannot use randomness. And intuitively for me, you can avoid dealing with the full generality of the problem by randomization. Often allows you to get away with the usual case. If you can get that to work, then randomization can sometimes do the rest. A totally different reason why randomization, and specifically this being correct most of the time but not strictly always, can help, is the idea of fingerprinting, or maybe checksums would be a better term. Fingerprinting kind of got stuck, but it's the wrong metaphor because from all I know, human fingerprints are actually unique or close to. You can identify an individual human being by the fingerprints. And this is totally not the idea of what fingerprints are used in computation or in algorithms. The idea is you take this complicated thing, the full human being, maybe the full genome, and you reduce it to something much simpler and smaller that's quicker to compare. That's the way the metaphor is to be taken. So instead of answering the full question, you answer a cheap surrogate question, but sometimes you have false positives. I mean, the other thing, this is also called hashing. Is the same. The implementation of fingerprinting usually is hashing. And that's what checksums also are in some form or another. So checksums, you would say, if you want to know if two files, long, big files are the same, you could compute some good checksum. And if the checksum's the same, chances are good the files are also the same. It's unlikely that there's a collision with different files giving the same checksums. That's a specific technique, but it's helpful so often that I made it a bullet of its own. And then the other reason is a bit more subtle. Maybe we'll see this today. Is sometimes you can prove lower bounds for algorithms by constructing an adversary that tries to make the algorithm fail by kind of modifying the input along the way. And by throwing in randomness in the algorithm, you make the algorithm itself less predictable. And so the adversary has less power. And that could mean that you can actually get stronger results. Typically, you can find faster algorithms or less costly algorithms using randomization. And you can prove any deterministic algorithm has to pay strictly more. There's another use case for randomization, which is also using randomized algorithms, but in a way has an entirely different goal of its own. And that's often called the probabilistic method. And this has virtually nothing to do with solving optimization problems and so on. Rather, you have some obscure object or object with certain properties where it's not obvious or not clear whether it should exist. And the idea is the proof technique says, okay, maybe you don't know. Let's try to design a randomized algorithm to construct such an object or to find such an object. And if you can prove that there's a positive non-zero probability that this algorithm succeeds, well, then there must be such an object. The trick here is that oftentimes this is much easier. There's various techniques. And it's non-constructive. It doesn't tell you how to exactly find this object or what it exactly looks like. It just proves that there is one. And because that's probably a bit abstract, I think it might be nice to have a specific example. And that was taken from Ramsey theories. Is kind of a whole area of specific discrete math results of this sort. Really, the gist of it is just this: you start with a complete graph on some number of vertices. And now I'm coloring the edges either red or blue. So every edge gets some color. And I'm doing this, I mean, this is very arbitrary. But every edge gets some color. And the claim is you can always find a clique of vertices that have all edges in the same color. Of size at least some bound that depends on n. And this is a lot of open problems connected to how exactly this R of n looks like, but I think you could take log n as a lower bound. I should have looked this up. So in my example, there's a triangle of the same color. For example, this red one. And I mean, if you think about this, of course, you can try to reason about this in various ways. But for graph of size 5, is it always possible to find a triangle of the same color? It's at least not obvious, right? It's not so clear. The idea of the probabilistic method would now be to say, let's design a randomized algorithm to find such an edge. And so I'm starting with the uncolored graph. I'm randomly coloring the edges. And then I'm trying to calculate the probability that my algorithm succeeds in finding such a monochromatic clique. And you can then reason over this algorithm a bit easier that, say, the expected number of such things it finds is strictly greater than 0, so there must be one. Okay, that the analysis uses things I'm going to introduce later, so I'm not going to do this now. But that's kind of the idea of what this probabilistic method looks like. And oftentimes, this is the only way we know to prove the existence of certain objects, which is pretty cool. On the other hand, it's also unsatisfying because it doesn't allow us to construct these objects. It just tells us that they exist. There's an obvious similarity between randomization and average case analysis. And this is really an undergraduate repetition that a good undergrad algorithms course will have drilled into you. But it's worth stating again just to make the distinction clear. Average case analysis can talk about deterministic or randomized algorithms, but let's suppose the algorithm is deterministic. So the same input leads to the same computation. I can still ask what happens for an average input. Randomized algorithms, the algorithm itself is not deterministic. It involves randomness and it generates the randomness. So it, even on the same input, does different computational steps. Average case analysis says, okay, the input is random and it's coming from some distribution. In randomized algorithms, our usual type of analysis, at least, will be worst case. We assume the input is the worst possible. But then we throw our random bits on it. And I guess it might be useful to say here explicitly that, because that term is also used sometimes, the adversary we imagine here is oblivious to our random bits. The person choosing the worst case input doesn't know what random bits we have. It's kind of logical because they're random, right? So how could they know them? But in theory, you could imagine that someone also can look at your random bits. And this is important to point out here. They cannot. At least they can't decide. They can choose the input based on the random bits. And then if we analyze things, the cost is given as an expected value if you do average case analysis, but the expectation is over the different types of inputs. If you do a randomized algorithm and worst case analysis, then the cost is also an expectation, but the expectation is over the random choices of the algorithm. So it's a different beast altogether, but the analysis techniques might still be very similar. Just because the randomized algorithm might effectively force the input to look like a random input. And so I guess here, one example would be a sorting algorithm might first shuffle the input to produce a clearly uniformly random permutation, and then it sorts. That's actually not a stupid idea in quicksort. Instead of picking random pivots in each step, you might, it's easier to program, at least, to first shuffle the entire list and then sort it afterwards. And then the sorting step can use standard choice of the pivot, maybe the first or last element, and nothing bad will happen most of the time.